I'm going to talk about Convergent Cluster Ensemble Analysis, or CCEA. It's Sawtooth Software's package for doing cluster and cluster ensemble analysis that will allow people to do segmentation studies. I want to give a little bit of background about segmentation because I think segmentation studies are the most difficult projects that we as applied researchers have to work on. And there's a couple reasons for this. One is that there are just an awful lot of possible solutions. Let's say we were in the position that we're never actually in real life. We have 1,000 respondents, and we know for a fact going into it that those 1,000 respondents sort themselves into just 4 segments. Again, we don't ever really know that for sure, but let's just give ourselves the benefit of a doubt and say that we did. Even knowing that information, there's about a really big number, about 10 to the 602 power, that's a 1 with 602 zeros after it, different ways of sorting 1,000 respondents into 4 segments. That's a really, really, really big number. It's a bigger number than there are atoms in the universe, okay? So there's just no possible way that if we harness together all the computer power on Earth, that we could look at all those solutions in any sort of real time. So what we do instead is we use some intelligent mathematical shortcuts to look at subsets of groupings that might be of interest. But again, because the sheer number of them is so great and the number that we're allowed to look at is so small, it certainly poses a challenge to us as researchers. The other reason I think that segmentation is difficult is that unlike a lot of the other things that we do, there aren't any statistical tests. It's not like we have a z-test or a chi-square test that says, oh, your data set has 5 segments in it, or your data set has 3 segments in it, or 7, or whatever. As a result, we never really know even how many segments are in a data set. And then even if we did, going back to the first problem, we don't know which one of those solutions is the right one because there's not a stat test that tells us which one is the right one. So for these reasons, segmentation involves a lot of searching on the part of the analyst. Over the years, one of the best ways that's been found to do that searching is called cluster analysis. And what cluster analysis does is it gives us a quick way to look for structure by looking at a lot of possible solutions. And there's different clustering algorithms or methods that perform this quick search in different ways. There might be hierarchical ones, or there might be what's called k-means that we'll talk about in a minute. But in essence, they work from the different clustering methods use different methods of data analysis, and they can help us come up with different numbers of clusters. And that allows us to get a feel for any real structure that resides in our data. One way of doing cluster analysis is called k-means cluster analysis, and it's a really efficient way of doing lots of cluster analyses quickly so that we can look at a lot of different candidate solutions. And the way the algorithm works is it identifies an initial set of seeds. So if we tell it, hey, we want to look at a 5-segment solution, what it does is it identifies 5 different seeds. And it calls them candidate cluster centers or centroids. And then in step 2, it takes each individual respondent in our space, in our cluster space, and it puts them, it assigns them to the closest seed. And then once we've done that, the algorithm says, well, now I have a whole set of respondents assigned to the first seed here. What's the center of that space where all those respondents are? And we have another set of respondents assigned to seed number 2, and it recalculates the center, and it says, these are my new candidate cluster centers, and then it repeats steps 2 and 3 until no respondents reclassify into new segments, and then it stops. Unfortunately, as you might imagine from an algorithm like this, k-means is a little bit sensitive to the location of the seeds that start the whole process going. Different seeds can lead to different solutions, so it's really easy to put together artificial data and show that k-means can end up at a very non-optimal solution. As a result, we strongly advise don't use simple k-means cluster analysis. It's a really good way, potentially, of fooling yourself that you found the true segmentation structure when in fact you have not. General purpose statistical programs, the SASs and SPSSs and SysStats of the world, They'll allow you to run k-means cluster analysis and several other kinds as well. But using those programs, you'll find that running more than a handful of solutions is difficult, and running hundreds or thousands of solutions is really impractical. They don't have the data management to handle that. They don't have the packages, the programs all packaged up to do that sort of thing. And as a result, you end up looking at a fairly constrained number of solutions, and you don't really get away from that problem of, hey, it's a really big universe of possible solutions, and I've looked through a mere handful of them. So what Sawtooth Software does is they automate this process and allow the researcher to look through hundreds or thousands of potential solutions with just a handful of mouse clicks that I'll illustrate in a couple minutes. The program includes two separate programs, one for Sawtooth Software's Convergent cluster analysis, a method that came out in the late 1980s, and one for a newer program called Convergent cluster ensembles analysis, using a new clustering technology that I'll also talk about in a minute. First, let's talk about CCEA, or Convergent cluster analysis. It came out in the late 1980s, at which time I thought it was just the neatest product out there, having previously tried to do cluster analysis with general purpose statistical programs. The neat things that CCEA does are it uses in it a variety of intelligent seeding strategies. So it says, gee, rather than just throw the seeds on there randomly, like some of those stats packages did, or if I want a 5-segment solution, take the first 5 records in my data file and call those my seeds. Those are really not good ways to do it. What CCEA does is it looks at a subset of the data, and it comes up with 3 different strategies. It has what's called distance-based seeds. It looks at a subset of respondents and picks, say, 5 of them that are really far apart in the space. And then it starts those as seeds. Or alternatively, it looks at a subset of respondents and looks for areas of particular density. So in this case, it might look for 5 areas that were, assuming we're wanting a 5-segment solution, 5 areas where the space is particularly dense with respondents. And alternatively, it runs a hierarchical based. It runs a hierarchical cluster analysis and then uses the cluster centroids that come out of that as the seeds to get the process running. In addition, it doesn't just do each of those things once, it does each of them 10 times. So the default setting in CCEA is to have 30 sets of seeds to start with. The neat thing that this does is it provides a measure of reproducibility of segments. Remember earlier we talked about we don't have any really good statistical tests to tell us how many segments we have or which solution within a given number of segments is the one to go with. This reproducibility measure is a measure of the robustness of a given segmentation solution. So it tells us how well the solution is capturing the same structure that other solutions are capturing. So it tells us if a given solution is an outlier or if it's one that has a lot in common with other solutions. And obviously the latter is what we're really wanting here. We're wanting a solution that captures real structure, not outlier structure. It turns out that this combination of intelligent starting seeds and lots of starting seeds and using reproducibility provided really robust solutions with a high likelihood of capturing segment structure. It just became a really good way of doing cluster analysis. In 2002, however, a couple of academics named Strel and Ghosh came up with something they called cluster ensembles analysis that in some ways took this idea of convergence a bit further. And it was introduced to the marketing research industry by Joe Retzer and Ming Shan at the 2007 Sawtooth Software Conference. What cluster ensemble analysis does is it starts by running a variety of cluster analysis models, and it's not constrained to cluster analysis. You could run latent class analysis models. You could run some cluster analysis models and some latent class analysis models, and produce a variety of different solutions. And those different solutions wouldn't even need to have the same number of segments. So you could run a 5-segment cluster analysis solution and then 6, 7, and 9-segment cluster analysis solutions using k-means, and then a 4-segment cluster analysis solution using a hierarchical method, and then a 5-segment solution using a different hierarchical method. In other words, you could use you could put into this whatever you wanted to. The neat thing about the ensembles analysis is it takes all those solutions that you generate with those various other methods, and it pulls them into what's called a meta-clustering algorithm. It takes the segment assignments that were output in bullet point 2 and uses them as inputs to create new clusters. As a result, cluster ensemble analysis was found to produce pretty robust results even when the inputs that we used in the second bullet point provided poor segmentation solutions, and it improved classification accuracy. So what Sawtooth Software did was it came up with its own meta-clustering algorithm that has all sorts of nice, fast-running properties, and we call the program CCEA, Convergent Cluster Ensemble Analysis. By default, CCEA uses 5 different forms of cluster analysis. 3 of them k-means with intelligent starting seeds that we talked about earlier with CCA, and 2 different hierarchical types of cluster analysis. And for each of those, the program runs 14 different solutions, one with 2 segments, one at 3 segments, and so on all the way up to 30 segments. And that provides a total of 70 input segmentation solutions. In addition, you're not required to use the CCEA defaults. Users can specify their own custom combination of inputs. You can either pick and choose things from the default selection, or you can include any combination of solutions that you've come up with on your own. So if you've run a bunch of latent class solutions, or you've run some latent class multinomial logit solutions, or whatever it is you've run using whatever other programs you like, you can put them in here and combine them all together and run CCEA on them, using those as inputs. So it's a nice flexible program. So before releasing the product, Sawtooth Software did some internal testing, and they looked at 7 studies using synthetic respondents that had known segment membership, and they found across those 7 studies that CCEA tended to outperform CCA in terms of reproducing known segment membership, which is good. At the 2009 Sawtooth Software Conference, Retzer, Alberg, and Yuan compared CCEA to 3 other ensemble methods and found it to provide superior performance. In fact, it was at parity with the top performing of the other 3 algorithms from the literature. So it's a really good, strong, robust way of doing cluster ensembles analysis. Well, that concludes our discussion of cluster and cluster ensemble analysis and of the Sawtooth Software CCEA program and how it works. I'd like to direct you now to part 2 of the presentation, which will be an actual demonstration of the software using some real data.